Okay, you are given an implicit function in this problem. Part A asks you to show that the derivative is equal to this particular expression here. So you have a way to just check your answer. So let's go ahead and take our derivative implicitly. I'm going to go ahead and rewrite the problem down here. So remember, the thing to keep in mind is when you take the derivative with respect to x, that's what we're doing here, the derivative of y is dy dx. So the derivative of x squared is 2x. The derivative of 4y squared is 8y times chain rule on the y. With respect to x, this is dy dx equals, the derivative of 7 is 0. And then I have to use the product rule here. So I'm going to separate it into 3x and y. The derivative of 3x is 3 times the second, plus the derivative of the second is y prime times the first. And then you just want to solve for y prime, so you can get all the y primes on one side, move everything else over, and then just factor it out, and you should get the exact same thing that they got. Okay, there's part A. Part B. Show that there is a point with x coordinate 3 at which the line tangent to the curve P is horizontal. As soon as you hear that word horizontal tangent, you should be thinking that dy dx, the slope is 0, and because this is a fraction, the only way that can occur is really when the top is equal to 0. 2y minus 3x equals 0. Okay? They want to know what happens when x equals 3. So when x equals 3, you end up with 3 minus 6 equals 0, so y is equal to 2. So this is the point that you come up with. Now, they want you to show them, so they ask you to find the y coordinate, which we did, but they want you to show that there is a point P on the function. So how do you show that a point exists on a curve? We're going to plug in your x and your y into the original function. So plug in 3 for x, plug in 3 for y, and what you should notice is, yes, that is a point on the graph because both sides are equal. So somehow you want to show that you've checked that. Okay, lastly, part C, they want you to find the second derivative, and then does it have a local max, local min, etc. So let's start with the second derivative first. So I'm going to start from here, and I'm going to go ahead and use the quotient rule. So the second derivative, using the quotient rule, the derivative of the top is 3y prime minus 2 times the bottom is 8y minus 2x minus the derivative of the bottom is 8y prime minus 2 times the top, all over denominator squared. Okay, that's it. You don't have to simplify anything. Now they ask you, does this curve have a local max, local min, or neither? Typically, when we have a function, we do a number line, but this is an implicit function. So I cannot do a number line because your derivative has x's and y's. How do you know which points to you plug in for x and the corresponding y? You're not going to be able to find those points, so this is where we use our second derivative test. So step 1 is check that at the point 3, 2, because they say use the point that you found in part B. So the point that you find in part B, is it equal to 0? And yes, it is, because we set it up so that's exactly equal to 0. So that tells you it's a possibility of local max or local min. Now we need to figure out the sign of the second derivative at that same point. Here's my second derivative right here. You're going to use x is 3, y is 2. Your y prime is 0, so you're going to plug in 0 anywhere you see the y prime, and what you're going to notice is you don't have to give them the exact value, but you should get a negative number. So either you show them negative 2/7 or say that it's negative. So you have a horizontal tangent. The second derivative at that point is negative, meaning the graph is concave down, so that means you have a local max.